I would like to thank everybody for being here, everybody who's joining us online. My name is Mario Romero. I am a senior associate professor at Linköping University. Recently, I was 12 years at KTH, and I'm also the national technical manager of the Swedish research infrastructure for data analysis and visualization in Previs. Today, I have the greatest pleasure of welcoming my PhD supervisor, my greatest mentor, Gregory Abowd, and we met at Georgia Tech. But as it turns out, he is now at Northeastern University, the Dean of the College of Engineering, Professor of Electrical and Computer Engineering. A few affiliated positions as well, but I did not want to go into every detail of that. Rather, I thought I would give you the cold numbers. Gary's thinking, what are these numbers? 31 years is the time that Gregory has been a professor. 26 and a half of them at Georgia Tech, where we met. 39 is the number of PhD students that Gregory has graduated in that period. 631 are the scientific publications that Google Scholar recognizes Gregory has co-authored.
And it's one short.
And it's one short. There's another one coming.
I'll add something.
But this is last night.
I know, something changed 2 months ago.
Okay. 56,631 are the citations that these publications have generated.
That's what changed. Used to be 66,000.
Really?
My book is no longer available on Google Scholar. So H-index is not a monotonically increasing function. Google controls it. Yeah. Took 10,000 citations away like that.
Oh, God. And I have a picture of your book. So at least
but that's not, Google doesn't find that relevant.
And this 98 is your H-index, which apparently has dropped. Do you know what that is?
I know what I have 5 of, but I don't know if it's the 5 you're talking about.
That's the most important number. Gregory, as an impressive researcher as he is, scientist, he's a family man. And he and Megan, his wife, have 3 beautiful children, Aiden, Blaze, and Mary Catherine. Gregory doesn't just collect numbers, he collects awards. And this is one this year for the service of being supervisor. Gregory got this award for supervising me and a bunch of other people. And it's super interesting because we have a bunch of KTH colleagues joining you in receiving awards this year. So we're in good company here. But I'd like to talk about an award that happened 2 years ago in Hamburg. This is Gregory giving a talk accepting the SIGCHI. For those of you who don't know, the largest professional organization of computing is the Association for Computing Machinery. And they have special interest groups. Special interest group for computer-human interaction. You can tell how old Kai is when the computer came first. Now we talk about human-computer interaction. But Gregory's here giving his speech, his acceptance lecture. And of course, he'll talk about his book, the HCI book. And of course, Gregory is going to talk about his achievements as a researcher, his innovations, the Aware Home being just one of them. But then he goes on and says, you know, I have all this stuff that I have accomplished, but the thing that I'm most proud of is this fact here. What do these 3 people have in common? Well, each one of them has won a Best Thesis Award at CHI 2023. And this is Gregory, they also have me in common. Because they've been supervised either by professors who were supervised by Gregory or professors of professors that were supervised by Gregory. So this gives you an idea of what I'm talking about here. And of course, when you're doing a good job in helping people, you're going to attract a lot of people, a lot of them good people. Gregory's here and we're all pointing at him. And this is just a snapshot in time because the family has been growing. Gregory recently told me that if you include all the PhD students that have graduated who have direct descendants from him, and all the postdocs and all the PhD students that are currently in the process, the numbering is closing to 500. And this is something that I just learned. I didn't include it in my slide. But here's the thing. Last night, Gregory reminded me of what is apparently the greatest compliment that he has ever received. Gregory, your gift, there's an R missing, is that you take struggling students and you make them good. You take good students and you make them great. And you take great students and you make them superstars. And apparently I said this a few years ago.
Where does Mario fit?
And yeah, where do I fit here? Where do I fit here? I'm a different category. It turns out that my PhD supervisor had left. So he took an abandoned PhD student and made him a Georgia Tech graduate. So it's my pleasure to introduce Gregory.
Thank you. Okay, quick little engineering feat here as I stop the sharing. Okay. Thank you, Mario. This is always, for me, the most enjoyable part. So, well, I don't know if you enjoyed it or not, but I hope it's not downhill from this point forward. So I'm going to explain why this particular title to the talk, and I'm going to deliver this in a two-act performance. So in the first act, I'm going to talk about work that started about 10 years ago that looked back at an old vision that has driven my research and the research of a large community in ubiquitous computing, that work of Mark Weiser. And it's always good in general as a researcher to look back at kind of visionary papers from the past and reinterpret them in the context of the present. And so that's what's going to motivate the first act of our story. We'll have an intermission where you can get yourself some coffee, and there'll be a little ad and entertainment. And then we'll come back to Act 2, where I talk about a different motivation for the work that I characterized at some point as the Internet of Materials. And we'll get around to talking about sustainable electronics. Okay, so Act 1, the setting is 2016. And I'm going to revisit the work of this individual. Now, I do not assume that this audience is all familiar with Mark Weiser, or specifically the Scientific American September 1991 article. If you have not read that, this is by far one of the most influential computer science essays of the 1990s, and it is still remarkably relevant today. So please take some time to read it. It's also a very enjoyable read, but it starts very eloquently with these two sentences. The most profound technologies are those that disappear. They weave themselves into the fabric of everyday life until they are indistinguishable from it. Now, when Weiser wrote this, he was talking metaphorically, that the notion of disappearing was because something would become so pervasive or common in your everyday experience that it would no longer demand your attention. And that's what he envisioned for computing around the late 80s in a project that he called the Ubiquitous Computing Project at Xerox PARC. Now, the main idea behind it is this notion that computers were not going to be a one-size-fits-all. There will be a wide variety of shapes and sizes and form factors and uses. And those uses will dictate different kinds of relationships between humans and the computing technology. And he did a remarkable job of predicting what would become commonplace within 15 years of the writing of this article. The end of the article had this other quote, not so true, that machines that fit the human environment, this is what he was envisioning, instead of forcing humans to enter theirs, the computer's world, will make using a computer as refreshing as taking a walk in the woods. And particularly if you've used any kind of projection technology, any kind of virtual conferencing technology, you would probably say that computing technology is not as wonderful as an experience as taking a refreshing walk in the woods. So you get some things right, other things you don't get right. But I had an opportunity in 2016 to reflect on this because I had met some colleagues at Georgia Tech, where I was at the time, who were from chemical engineering and from material science, and they had been told to come talk to me about some work they were doing. They were starting to show that they could grow in the laboratory transistors, billions at a time. And they thought this was really interesting from a technological perspective, but they had no idea why the world would care about this. And I said to them, have you ever heard of Mark Weiser? They said, of course, no. I gave them a copy of the article, and I said, you just need to read the first paragraph, and you will understand why I am so excited by that particular idea, because these individuals from outside of computer science were giving me an opportunity to rethink what that vision that was at that time 25 years old, what it might mean in the current context. And what it meant was that I could rethink the kind of premises underlying ubiquitous computing. Now I'm getting the delay issue.
Press the keyboard.
Yep. So also a little later, but around the same time as ubiquitous computing became a thing that drove computing research, what was driving industry work was a phenomenon called the Internet of Things. So I did some Google searches, which is what you did in 2015, to say when you think Internet of Things, what images appear? And this is a common kind of image that would appear. And when I looked at that, I said, okay, that's actually an Internet of computational devices. So then I did the next thing. I Googled things. And this is the kind of picture you get. And some of these things are, technology, computational. Many of them are things that you don't connect to things that are computational. And I said, well, what would it mean to provide computational capabilities in these kinds of things? So that's why I was motivated to try to imagine. So I had this term computational materials that then became Internet of Materials. I wanted to call it Internet of Things, but that was already used for something else. So I coined this phrase Internet of Materials and wanted to say, well, what does that mean? So around 2016, I tried to position this within my research group about these ideas that we might pursue. And it came in two ways. How can you look at what I refer to as cheap things in the world and make them computational, and the reverse? So the first exercise, cheap things in the world. Here's an example, a Post-it note. You buy those hundreds at a time, and each one costs fractions of a penny. And they have many, many, many uses. But I think most of us would agree that none of those uses would qualify as being computational. I said, well, what if you could produce something that was computational connected to this thing that was like a Post-it note, so an electronic or an e-Post-it note. So this was proposed as something where if you touched that little red button and spoke, what you spoke would be recorded and delivered to some individual. I think we would agree that that is a computational capability. But how would you provide that computational capability, but do it in a way that would be as cheap and as ubiquitous as a Post-it note? That was a challenge. In 2016, anyone who had any kind of maker capabilities could rig together something using Arduino or other kinds of electronics, something that you touch it, you speak to it, it records and sends it, but it probably wouldn't be paper-like. It certainly wouldn't be thin and flexible, and it absolutely wouldn't be cheap to produce. Cheap on the scale of what a Post-it note costs. So I said, how could we do that? Or could we do it? But the other way around, again, this is 2016, take a piece of consumer electronics technology. This is a version of a health tracker. This was, I think, the Fitbit 2. You could charge it, would last about a week. Wear it on your wrist and forget about it for a week. And it would track simple activities like number of steps you've taken. So I said, well, what would be something where you take something that's computational and you would make it cheap and more like things of the physical world? So many of us are familiar with these silicone wristbands. You can get in many different colors, have things printed on them. Make them in bulk, they cost maybe about 4 cents each. So relatively cheap, waterproof, no thought of ever charging it. So what about something that I refer to as the infinite bit, which essentially was a wristband that would do the activity tracking, but would be the cost and the material property of the silicone wristband. So these were two ideas of, they asked the question in 2016, can we build something like that? And the short answer is that in order to do that, you had to think about 3 different design priorities or dimensions that typically were not the motivation or emphasis simultaneously of most computing activities. So from a power perspective, you had to think about, I don't want to have to deal with charging something or changing batteries. So the principle, never change a battery, right? You have some way of powering this entity. From a cost perspective, you have to be able to manufacture it at scale in such a way that it would be cheap to produce in large numbers. And finally, it either has to look and feel like a regular object of the physical world, or if you attached it to an object already existing, it shouldn't change the look and feel of that object. Okay, so looks like everyday material. So those were 3 design dimensions that we said, in order to achieve that vision that I was suggesting, you have to pay attention to all of these simultaneously. We did it. Now, we did it. From the perspective of a researcher, which I was talking about this morning, what is research? Research is what researchers say it is. So we did it, meaning we convinced other people like ourselves that we could accomplish this. I'm going to highlight the work of 2 different research teams. So this first one, Nivedita Aurora, was a Ph.D. student co-advised by myself and Thad Starner. And Zio Wang was a world-famous material scientist who was at Georgia Tech. And he had introduced this notion of triboelectric nanogenerators, which is a very fancy way of saying, you know, when you take a balloon and you rub it on your hair, you build up static energy and it will stick. Well, if you could harness that phenomenon in such a way, if you take 2 materials and you have them constantly touching each other and separating, and then you had a way to rebalance the static electricity that was produced when you brought them together, that's the triboelectric effect. The nanogeneration is allowing a balancing field. If you did that back and forth, you could essentially capture an alternating signal, an AC signal. And that AC signal is related to the vibrational source that's causing the back and forth. Your voice is a vibrational source. So Saturn was an example of what Nivedita invented or presented. That was a multi-layer material, paper, plastic, and copper. So relatively simple materials, although not necessarily the cheapest materials. But when you bond them together in a particular way, it was a thin, flexible material, and that is the sensor. So it uses the vibrational energy of your voice to record your voice. This is a printed antenna. In the presence of a radio field, an antenna will reflect that radio field. If you modulate or modify the characteristics of that antenna, then you can reflect a signal back that encodes some information. Well, the vibrational energy sensing that the Saturn patch produces is the modulation key. So essentially, this thin patch material is a wireless microphone. Speak into it, and it can transmit the signal wirelessly. That's close in spirit to the e-Post-it note I was talking about. And this front piece is paper. You actually can write on it, okay? So that's one example. The next example, the infinite bit. So when you walk, your arm sways, a natural walking pattern. Your body blocks light from one side to the other side. So if you have something on your wrist that could capture the changing light patterns, you could determine walking patterns. So this platform, OptoSense, was created using a flexible substrate onto which 8 different photo sensors were placed. And this black material is commercially available photovoltaic. It harvests energy from indoor light. So that harvests enough energy to be able to read the signals on the 8 different sensors that would then be fed into that little module that's a Bluetooth module that sends the signals to a nearby source like your phone. And it could, the pattern of light detected on that signal would essentially produce a time series that very easily you could break into steps. And it's powered by indoor light. So that's getting toward the infinite bit idea. Right? So I thought, okay, this is good. In a period of 3 or 4 years, we showed examples that had promise toward the computational materials or the Internet of Materials. So 2 points I want to make here, and then it will be the end of Act 1. What lessons did I learn? Well, many people here are human-centered researchers. When we think about how technology can serve human purposes, we try to start with understanding the people and the problems and the opportunities to support their everyday activities. And then we work our way down, depending on what kind of research and what we want to be able to do. But in my world, you would think about what applications would serve those people. How would you build those applications as essentially algorithms that run on some computational system? But that computational system has an operating system, functions that you can call, and that operating system is run on silicon circuits, and those circuits are made up of computational devices. And that's typically, in ubiquitous computing, where we would stop. But my experience with these 2 examples showed that you needed to go beyond that. You needed to think about how things were assembled, the fabrication techniques, because you wanted to manufacture them at scale and at low cost. But you also wanted to have other features like the TENG of that Saturn patch required certain kinds of materials be used. But most computer scientists don't go down to this level. And so the lesson learned that is if you want to be making progress along this line of Internet of Materials, those 2 examples and the 3 or 4 other examples we had at that time made very clear to me that you had to have knowledge in all of these areas to realize those examples. So you either have to get that expertise yourself, or you have to work with people with that expertise. So I'm old and decrepit and beyond being able to learn anything new. So my option is always to find other people with that technology. Mario will say that's how I've been all my life, and that's probably true. But I wanted to inspire individuals wanting to advance this area of Internet of Materials to learn these things themselves. So I got up on my soapbox and said to computer science people who design curriculum, computer scientists need to understand materials, and they don't. So this evolution or revolution in computing required an adjustment of the mindset of what's the body of knowledge that computer scientists should have. That's the first lesson. The next one, not so happy. Because I would go on the road, show these ideas out of the ePost note, infinite bit, and I'd be, wow, look, and we did it. Here's some examples. I could show it. I went to Google and showed them demos. And after a while, people would say, that's really interesting. But why do we want electronic Post-it notes? Why do we want the infinite bit? And so our hero had a dilemma. And at that point, the curtain comes down. End of Act 1, and we have our intermission. So I'd ask you all to kind of stand up. There'll be drinks in the lobby. If you've ordered them ahead of time, you may pick them up now. And while you're milling around, I'll either take questions or I will deliver a word from my sponsor. But you know, I'm Dean of College of Engineering at Northeastern. I can't go anywhere without talking about Northeastern and without wearing things that reflect Northeastern. I'm a walking billboard. Most people know about Northeastern, at least in the US, because of its superior co-op program. As I said before, 115 years old, and it's a form of experiential learning, which is extremely popular among students. Northeastern has the largest number of undergraduate applications in the country among private universities. 105,000 people applied to be accepted into our undergraduate program, 6,000 seats. So selective. But what they don't know is that Northeastern, they think, oh, Northeastern, it's that small university in Boston, you know, near all those other bigger and more famous universities. They may be more famous. I don't think they're bigger. We have like 44,000 students. And part of that is because we're not just located in Boston anymore. Over the last 12 years, we've developed campuses, 13 in total, 12 in North America, and 1 in London. And we're about to open up a 14th campus in New York City. So we're both experiential and global. End of commercial. Ding, ding, the intermission is over. Curtain opens up. We play the interlude of all the musicals that you love to the songs in the first act, and we'll come back to Act 2, titled Renewed Inspiration. So it turns out I had the right idea, but for the wrong reason. To recap, when we ended Act 1, our hero was having an existential crisis because he had what he thought was an interesting trajectory of research, but a very poor motivation for it. And so what I want to do now is reflect on why I had that motivation. So the initial motivation for Internet of Materials goes back to Mark Weiser. And again, I want to remind you that, don't worry about these bottom two. That article is the one you should read, the one by Mark Weiser. And how he pitched ubiquitous computing was as the third generation of the evolution of interactive technologies. The first being mainframes, started in theory in the mid-30s. About 30 years later, the personal computing revolution started at Xerox PARC and other places around there in the late 60s, so about 30 years later. And then about 20 to 30 years later, Mark Weiser suggested this era of UbiComp with a very American-centric metaphor, that the different sized devices he put into 3 classes: the inch, the foot, the yard. I was talking to Mario this morning, and I said, for this audience, maybe we talk in threes, which is what I always lecture about Weiser. And so it's 3 centimeters, 30 centimeters, 300 centimeters. He said, no. And he had a better way of thinking about it. But what's important is that at the different scales, there are different kinds of uses, and there's a difference in the relationship between the human and that technology. When you have something so small, you can put it on your body or carry in your pocket. It's with you all the time, right? And you all have 1 or 2 or 3 of these kinds of technologies. Something that's a little bigger, like a tablet computer, you can walk around with, but you don't have it with you all the time. It's just easy to pick up and co-opt. And maybe you share it with other people, or maybe it's yours. You get even larger, big displays, particularly ones that are interactive, they're usually fixed in place and there to serve an audience of individuals. And that was his point, that computing will have many different shapes and sizes, different functions. Isn't this great? And there'll be so many different varieties of these that we won't even know where all the computing is in our environment. Okay, that was one of the motivations. But what caused these technologies to be interesting to me was to think, okay, well, in the mid-2000s, I said, we're 20 years from when the first ideas of UbiComp came about. Certainly, there has to have been some things that Weiser didn't think about. And so I wrote an article, and I talked about technologies that emerged in the mid-2000s that were not really what Weiser talked about. And then by 2020, this article was something that was kind of a post hoc rationalization. I didn't invent anything. I just observed what was out there. So I said, well, I actually want to be like Weiser. I want to think about things that could be. So I forced myself to say, oh, by 2020, what revolutionary technology could come about? So that's what was motivating to talk about these computational materials, or what became the Internet of Materials. But here's my mistake. What happened in all of these generations was there was an initial application that motivated companies to invest and create the technology, and consumers to buy the technology. So mainframes with scientific calculation during war to calculate ballistic trajectories and things. That's what motivated the development of mainframes. Personal computers was the spreadsheet in business settings to essentially take the metaphor of a ledger and make that electronic. That's what caused businesses to adopt personal computers. What caused UbiComp to be adopted, at least at the inch scale, were these personal management, calendar management applications, right? You'll say, oh, but we use it for so much more. That is true, but those were what I call follow-on applications. After you've already got the infrastructure, what can you build on top of it? when I talked about this post-UbiComp cloud, crowd, shroud, I talked about services that happened that drove the adoption of these technologies. And so I'm thinking, I have got to come up with the initial applications that would motivate Internet of Materials. And so I was obsessed with coming up with these kinds of applications that you would want. And what happened? I failed at doing that. Just like when UbiComp started and people said, what's the killer application? I hate using the word killer application because literally what drove the mainframe was killer application. So I don't like that. I talk them initial applications. And people always wanted to know what these were that drove people, companies to produce it, people to buy it. So that's what I was doing. That was the rabbit hole I fell into. And I just wasn't good at predicting that. So the e-Post-it notes and the infinite bit were never going to cause the Internet of Materials to become a common place thing in the coming years. But that's why I went down that particular path. Now, 5 years later, much more, a lot of wisdom and a lot of experience and a lot of other smart people telling me what's a better idea. There are a number of better motivations for Internet of Materials. I'm not going to talk about these top two. I can, if you want, after to say how these are better motivations. I'm going to talk about what I think is the most important reason to pursue what I was talking about, and that's a sustainability argument, or what I now refer to as sustainable electronics. So let me build that story. It's important to understand what was driving Weiser and others in his time to have this view of optimism about where computing was going to go. And it was Moore's Law that many of you are probably familiar with. This is the original wording of Moore's Law in his mid-60s paper, where he pointed out empirically there was evidence to support the fact that every 18 months or so, the computing technology was going to become cheaper and more powerful, but basically we'd be able to pack more computing power, transistors, into a smaller space without incurring larger cost. So a doubling due to increasingly clever ways to manufacture integrated circuits. That was the key. So I have some good news and some bad news about Moore's Law. We'll start with the good news, obviously. So it is true that if you look at the progress of manufacturing these integrated circuits, the price of this technology has dramatically decreased. And I'm showing you probably a very odd way of quantifying this progress, but it's because it came from my colleague, Mike Filler, who's a chemical engineer, one of the two individuals that came into my office in 2015 to talk about a new way of manufacturing transistors. So how many of you studied chemistry? Okay, so am I going to put you on the spot? I am. What is a mole?
I took the exam.
Okay, you took the exam and immediately forgot. That's. I'm glad to hear that that's not just the hallmark of the American education system. That's a yes. It's a number, but what is the number?
It's the number of molecules that
10 to the 23?
Yes, it's 6.023 times 10 to the 23, otherwise known as Avogadro's number. So Mike was saying that if we measured the cost of computing in terms of how many dollars it takes to produce a mole of transistors, and we plotted that over time, you will see that it was pretty much close to $1 to produce a 10 to the 23 dollars to produce 10 to the 23 transistors. Now you may say, that's a lot of money. But you may also say, when will I ever need 10 to the 23 transistors? Okay, fair. But if you plot it that way, you see drop in orders of magnitude over a few decades, the cost of transistors. So yes, the cost of computing has gone down dramatically over this period of time. However, we're also used to seeing Moore's Law expressed this way. And in fact, it's expressed this way in such a way that we're not even sensitive to this anymore. So this is a technology, the Apple iPhone 5 that came out in around 2015 when I started looking into this. And you'd see statements like, oh, you buy an iPhone 5 today and you have in your hand something that is almost 3 times faster than the most powerful computer on the planet 30 years ago. And we're used to that. We're numb to this kind of progress. And I was talking this morning about this. So there's some examples I'll talk in augmented reality and visual reality. This advances our computing dreams. And this also makes us lazy. So what I'm going to show here in personal computing, mobile telephony, augmented reality, virtual reality, images of the early prototypes in that space. Not quite so early here. This is just personal. This was the laptop computer I took with me to graduate school in 1986, right? And it cost about $5,000. And it was fantastic because it had a 10 megabyte hard drive. It's a lot. And it had a 9-inch screen that could show 2 colors, green and not green. and you could carry it around, and it wasn't much heavier than a portable sewing machine. So this was fantastic. This is the early mobile telephone. One of the first examples at Columbia University of augmented reality. So as you can see here, the very svelte packaging of a little backpack here, an antenna sticking up here that was the GPS receiver, some very unobtrusive glasses, a simple way to interact. I'm being facetious, a very clunky way to overlay monochrome graphics onto a scene in front of you. This is one of the first examples of virtual reality. What you don't see here, only hinted at, is this little umbilical cord that connects to a mainframe computer over here that essentially renders very simple graphics into this set of goggles, right? Those are the first clunky examples of those technologies. But if you look at all of those areas 30 years later, then you see the advancement of things that were cheaper, worked better, more functional, sleeker, more user appealing. And my point is that there wasn't really an innovation in the idea of how to use the technology. There was just Moore's law that advanced things. So I refer to this as Moore's law thinking. And here's what it means. You're sitting down with your advisor and you have an idea. You know, when Blair McIntyre, who worked at Columbia, had an idea about doing augmented reality, and he talked to his advisor, Steve Feiner, he showed this monstrosity of an AR infrastructure. And Steve's reaction is, don't worry about the fact that you're breaking your back carrying all this thing and that this whole piece of equipment costs, you know, $50,000 to put together. And the graphics aren't very nice and they're not very well registered to the scene. Don't worry about that, because Moore's law will solve that. You won't have to. So all you needed to focus on was a new idea of how computing might be used. That's what I refer to as Moore's law thinking. And it's based on this assumption that computers will always get smaller, cheaper, and more powerful. That's what Moore's law was about, right? So the key insight here, why, is because of what Moore said, clever, integrated manufacturing techniques of integrated circuits. Okay, now the not so good news. The cost, which I said was good news, the power, and the waste. So I said this was great progress for transistors, but if you look at other things that humans manufacture, these are various molecules and chemicals that we manufacture, their cost is dramatically lower. Now, you can argue that a mole of aspirin molecules is not comparable to a mole of transistors. I don't want to go down that rabbit hole, right? Because yes, I'll agree, but I'll argue that, you know, we'll never have a mole of transistors because it still costs quite a lot of money to produce that. So we can't even think of what we could do with that number of transistors because we can't afford to manufacture them. But this brings up the question, why are these things so different in their cost? Well, the answer is how they are made. Fully integrated manufacturing techniques. So, typical modern integrated circuit manufacturing plant involves thousands of steps, each step following the next. That's what integrated means. You do the first step, then you do the next step, blah, 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 blah. If you want a good yield, which means at the end of that manufacturing process, you get things that work, then you have to look at the yield of every single step, and that's multiplicative. So if you have 50% yield in the first step and 50% yield in the second step, what is that? That's 25% yield after only 2 steps. So if you want 90 or 99% yield rate at the end of thousands of steps, each step has to be 99.999999 impressive in terms of its yield rate. That is very difficult. We've done it, but it's also very expensive, which is why very few companies can afford to do the next generation of integrated circuit technology. On the other hand, these technologies use a process that I'll refer to as modular manufacturing. But the way to think about that is typically there's some kind of chemical reaction that happens that produces lots of different kinds of things, products. And some of those you want to pull out, the ones that have the same kind of characteristics. So you do the chemical process and then you filter out to get the things that you want. And if you're really good at doing that, all of the results of the chemical process, everything has some use. So you've just got to do the right kind of filtering and then figure out the application for all those things. Petroleum engineering is a very good example of this. All the different products that come out of a petroleum refinery that serve many, many different kinds of industries. It wouldn't work if it just served one kind of industry like gasoline, because it would be too expensive and there'd be a lot of waste. But no, the other products produce plastics and other kinds of things. Okay, so it's just a different way of manufacturing. So from a cost perspective, it costs way too much to manufacture computers the way we manufacture them today. Next, not so good news. It takes way too much power to power things that are computational. Estimates by 2030 are that about 3% of the world's electrical supply will feed data centers. Now you may think 3% is not a lot. 3% is a lot of our world's electrical supply. Just to feed the data centers. That's not even talking about these kinds of devices that we have in our everyday life. Furthermore, if you don't have the luxury of the computational device being stationary, you can't plug it in to a constantly supplied power. So if you do, like a big data center, you can imagine using renewable sources of energy. So it doesn't matter, in some sense, how much energy it takes because you're getting it in a way that's more environmentally friendly. But for electronics that move around, our options are to recharge it occasionally or to have batteries that you replace occasionally. Recharging occasionally is okay if you have one device. If you have 2, 3, 5, 10 devices, it starts to become a little annoying to have to remember to charge things, particularly when you travel and you forget all the adapters, right? So it's an annoyance. If you have to change the batteries, the problem is, what do you do with the battery when you're finished with it? That's the next problem. Batteries, as well as old computers, what do we do with them? For the most part, we throw them out. Arguably, when they have much of their infrastructure is still reusable. It's just not easy to reuse it, and we, for the most part, are lazy, and so we dispose of it. And so the largest growing form of waste in the world today is electronic waste, and it's only growing. So we have cost challenges, we have power challenges, we have waste challenges, which leads me to the title for this talk, Ubiquitous Computing, Considered Harmful. Now, I'm considered one of the founders and leading lights for ubiquitous computing. Why on earth would I want to criticize the community that has brought me to this level of success? Because you only get better by questioning things about yourself. And you need to do that. So here's the argument. Our reliance on all things computational and digital appears to only be increasing. And particularly if you're coming from a capitalist mindset, there's every motivation to do more and more computational things because it opens up other economic opportunities to gain wealth, right? So it appears that we're not able to stop that insatiable need for more things computational. That's one piece. I hope I've set the stage for arguing that the way we go about manufacturing and operating things that are computational threatens the planet. We have to stop that, or it will stop us. So if you accept those, and I'm happy to enter into a debate about whether you agree with either of those, but that's where I'm coming from. So if you accept those, then I think the only option is to think differently about how we create things that are computational. What are the things we need to challenge? How things are powered. The two examples I gave at the beginning were really focused on operational power needs, making things self-sufficient in their operational mode. But anyone who knows anything about life cycle assessment knows that that's not the only place you use power. You use power in getting raw materials, in manufacturing, in distributing, using, and then disposing. So I was looking too narrowly at the power question. We have to question the materials that we use. I talked earlier about how different materials allowed you to create things that were operationally self-sufficient, and argued that you needed to have knowledge of materials in order to be able to do that. But I'll also argue that if I'm using Arduino to build a little prototype, and I want this prototype to be biodegradable, I can't do it because the elements I'm starting with are not biodegradable. So if I want to worry about those kinds of issues, I have to think about different materials. We have to think about the process through which we manufacture. I argued that the manufacturing process of integrated circuit manufacturing is one way to create computational things, but has its challenges. We have to think more about the life cycle implications, not just in the operational phase, but in the mining, manufacture, distribution, use, and end of life. So now what I'm going to show you are two pieces of work. These are things that I've worked on in the last year, neither of which is published, but I'm sharing with you anyway because I feel smart people will take good ideas and do great things better than I will. Really simple example that's going to look at questioning the materials we use and the manufacturing process. So if you've ever built a prototype using Arduino or other electronics, you probably are familiar with the technique soldering, that's both a noun, solder, and the process, soldering, where you attach an electrical device to a circuit so that it will hold and will conduct electricity so the circuit will work. It's surprising to me that we have never really questioned soldering in the electronics manufacturing world. Done lots of things to make it fast so it can be used in lots of different high throughput things, but we haven't really questioned the soldering itself. Yes, there's some low temperature solders, but not much advancement in soldering. And the one thing that soldering makes easy is a way to attach things. But if we think on the flip side, the one thing soldering makes hard is detaching. So you got to heat up each point, and then you still got residue. It's not so easy to take apart something that's been soldered. Now, a couple years ago, there was this clever paper that was in CHI. So this was CHI last year, but the work was done about 2 years ago. And their idea is, well, what if we get rid of soldering to hold things together, and we just use pressure to hold things together? So their brilliant idea was you've got a circuit board, and you have some circuit elements, and you want to make sure that they get placed and held down so that the circuit will work. So once you've got the circuit, you can take an image of it, you can create a 3D model, and you can print a housing that goes above and below, and you screw it together, and it clamps together the circuit. When you want to stop using that prototype, you unscrew, and you take off the elements fall off the board, and you can reuse all those elements. Great idea. A horrible way to solve that problem, because you have to manufacture this housing for every different circuit. So I, with one of my only postdoc, Nargis, came up with a better idea. But we had a naming challenge. I said, Nargis, we've got to give this a name that is both a noun and a verb. So, ladies and gentlemen, I introduce to you Proform. Proform is the process for being able to replace soldering. And to do this, you proform a circuit together. But it's a very simple idea because it uses a device that already exists today. Anyone here ever done vacuum forming? You put something on a surface and there are holes in that surface. You have a malleable or heated plastic, and you suck down, and that will come down and will cover the object that's under it. Well, there's a reverse of that called thermoforming. That's where the form part of Proform comes. The pro is prototype thermoforming. You push down from the top. Lots of advantages to doing that. You heat a thermoplastic and then you push it down with a certain pressure and it wraps around the things that are in the area. That already exists. So we said, well, what if you thermoformed a circuit rather than soldering it? So I'll show you a quick video to show some examples and some advantages. So here, Nargis is placing electronic devices onto the circuit. That's the plastic, the thermoplastic, placed in the housing of this commercial machine. That heats up the thermoplastic, put it in there, close it, and voila, 90 seconds later, you open it up and cut away the excess plastic. We'll come back to that if you want. And you have a working circuit. That's just a photo detector, right? There's no solder. So when you can rip that off fairly easily, take the components off, put it onto a different circuit board, put it in the machine, proform it, and voila, you've reused those elements. Now, the thing that's important is that thermoplastic is just a piece of plastic. So you don't have to do anything special for any given circuit, right? So this is a reuse. You can do multiple circuit boards at the same time on this base. I would challenge you to simultaneously solder 4 circuit boards. In fact, I don't encourage you to try doing that. You can repair something by using a hot gun to essentially cut out, or this is showing exposing something that you would want so you can interact with it. But you can also repair something. If one particular element of your circuit isn't working, you can cut around that piece and then thermoform again, put in a new piece and thermoform it again. So it's much easier to do that kind of repair. So we got repair, reuse, recycle. You can encapsulate something by doing thermoforming on both sides or proforming on both sides, and now you get something that's waterproof. Waterproof and blinking LED, it's working. Wow. Interestingly now, you no longer have to separate creating the form factor of something from integrating the electronics. You can do that at the same time. So this is an example of proforming over a mold and a circuit to create something that has a shape and the embedded electronics. I can give you more interesting examples. I'll end with this to show that you can do things with proforming that you cannot do with soldering, right? You can proform something in a vertical position. Try doing that with soldering. You can do it on an angle. You can do both sides of something simultaneously, and you can do it on curved surfaces. All of these things are difficult, if not impossible, to do with traditional soldering. So what's interesting and why I'm making a big deal is at the end is that though we came into proforming from a sustainability argument, it turns out it has other advantages over the traditional technique for bonding a prototype together, which is soldering. So that's the first example. Second example, how do you influence consumers? How do you get people to make sustainable choices at the point, at the time when they need to make a decision? And I'll give you an example, and I was talking about this at dinner last night. We're used to seeing these kinds of nutrition labels, right? And so we can compare 2 similar food products based on elements of nutrition that someone has deemed are important. And we trust these because there are usually regulatory bodies that dictate putting truth on these kinds of labels. If we think about life cycle assessment and all the things that go into the sustainability of any kind of product, it's very difficult for us as consumers to understand what are the life cycle implications, getting to the point where this thing I want to buy and down. That's very difficult for us to know about a single item, let alone comparing 2 different options. And the reason is because life cycle assessment is a very specialized, very expertise-driven and time-consuming activity to do correctly. So what if it were easier to do a life cycle assessment and faster? And to date, there is no way to do this quickly with any sense of reliability until now. So working with some colleagues at the University of Washington, Zihan, who worked with me at Georgia Tech before I left there, now is a Ph.D. student with Shwetak Patel and Vikram Iyer, created a browser plugin that you can point to a web page. This is the iPhone 16 web page, and I know this is difficult to see, but what it's showing is in terms of number of trees chopped down or amount of embodied carbon or other measures, what does this device represent in terms of its entire life cycle assessment? And the way it does it is by mining lots of sources around there and using large language models to get within 90% accuracy of what a detailed LCA would produce. So it's not perfect, but it comes in seconds and it's pretty close. The other thing it does, and that's what this window is showing, and I'll show a video next of other examples, it's comparing the iPhone 16 to the Samsung Galaxy 23 or 24. Right, so it's showing how does something that's functionally similar compare against something else from a sustainability perspective, and delivering that to a consumer at the point when they might be considering purchasing something. It's like the nutrition label that's delivered to you by a third party. So the question is, do you trust that third party source? I'm going to show you a video that shows this in other examples. First example is I'm reading a research paper, and I've highlighted the part in that paper that talks about the various elements that are being used and how they're being manufactured. So you see in green here, the little plugin has highlighted the things that it thinks are important in terms of the materials and the manufacturing process, and it shows you an environmental assessment of it and gives you this what-if capability. First of all, you can change what it's compared to trees, cut down, beef consumed, carbon emission. But you can also fiddle with the recipe. This gave a ratio, and it says, well, if you adjusted that ratio, how would it affect the environmental impact of that particular thing? So you could see as a researcher, you could figure out, are there more sustainable ways to achieve the same outcome? Right? So it's looking at all the different kinds of elements and the fact that this is being manufactured as a woven glass fiber sheet. So it's helping you look at someone else's work and put a sustainability lens on that to inform what you might do in the future. This is an example of, I want to order something and I want to use FedEx or I want to ship something using FedEx. So you give it the size of the box, you give it the from and the to, and it shows the different costs. This is what happens on the FedEx site. But now the plugin will show you which are the ones that are most eco-friendly and will explain to you why they're more eco-friendly. So in addition to seeing the dollars it will cost, you can see what's the impact environmentally of those particular decisions. And the point about this is it's delivering it to you at the time when you're to make a decision. Now, I'm not arguing, and this is another example. I said, if I'm doing machine learning, what's the cost of using this, doing the training or using this large language model? So it says, here's the processor I'm using, and this is how long it takes to do the training, and it lets you see, well, what's the impact of that? And what if you change the processor, or what if you change the amount of time? So it helps make a machine learning researcher have the knowledge to determine what the environmental impact is of the work that they're doing. These are all things that can potentially influence consumer behavior. Someone trying to buy consumer electronics, a researcher in material science, or someone in machine learning. And I'm not going to say this is the best way to do it, but the stage is set now to say, well, what do we actually need to deliver to people in real time that would influence their behavior? And we did not have this capability before, having access. And this even tells you how expensive is it to do this sustainability analysis, because we're using modern AI technologies to do it. Okay, so very excited about this kind of work. I'm also excited because I'm well past my prime. The best thing in my life is to inspire people to go in a particular direction. So a lot of what I'm talking about is to try to inspire people to say, how might you lend to this sustainable electronics agenda, if you believe that's the right kind of motivation. And there's a growing community of people doing this. Neha herself had a paper in sustainability at this last CHI conference, along with a number of other papers. So I'll leave you with that, to say that our hero is now happy at the end of Act 2, or at least he feels that he's done something, he's doing the right thing for what he hopes is the right reason. You may agree or disagree, and if you disagree, that's great, because I would love to engage in a conversation, and thank you.